下一位我们邀请的是挺著名的一位AI 领域的领导者哈 ，Daniel Povey 啊，好，那我先用中文介绍他吧哈。Daniel Povey 教授是著名的语音识别开源工具卡蒂的主要开发者和维护者，被称为卡蒂之父。卡蒂集成了很多的这个语音识别的各种各样的能力哈，是公认业界语音识别框架的基石被广泛用于所有的工业界、学术界几乎这句我觉得是无可置疑的，几乎所有语音团队都使用卡蒂引擎来开发那个语音相关的智能解决方案这个 paper 被引用了6000次，论文这个也被引用了36000次还对语音识别做出了许多科学的贡献为了尊重那个 ，sorry， OK， 好
，Okay, let me do share screen.
Okay, so let's welcome Daniel Povey. I just finished the introduction to you, and welcome Daniel, and he will give us a presentation about the progress in ASR with the next generation Kaldi. Thank you, Daniel.
Thank you. Okay, so this is what I'm going to talk about. I'm going to briefly describe like what Next-Gen Kaldi is and who the team is and what we're working on. I'm going to give you a brief summary of some of our recent like technical work and recent papers we're publishing about accelerating RNN-T. But then most of this talk, I want to describe something else that we haven't yet published, although I guess this technically is a kind of publication. It's about a reworking of the conformer encoder, which is conformer is just a modified transformer. This is a lot more technical than the other talks. I'm just trying to find something that I think is going to be interesting to most of the participants in this conference. So you'll when I get to that part, you'll see what it's all about. But so let me start with the Next-Gen Kaldi intro. So the Next-Gen Kaldi actually describes this cluster of three different open source projects. Actually, these are just the main ones. We have a bunch of smaller ones that kind of implement extra features for them. But so LayerNorm is all about data preparation for speech recognition. It's like, so in speech recognition, the data preparation is much more complicated than, let's say, computer vision and things like that, because the utterances are all different lengths. There's all kinds of issues about how to put them in batches and things like that. Like, we've made a whole repository about that to keep it separate from everything else. Then K2 is a bunch of core algorithms in C++, things like lattices and finite state transducers. And then Icefall is the recipes. And right now, most of our effort is going into Icefall. And Icefall is developing very rapidly. It's not super stable. You know, we change the recipes every week or two, but we've structured it in such a way that we can make rapid progress. Later on, we'll clean it up a little bit. Okay, so this is the team. First, on the left is my very talented team here in Xiaomi. Most of LayerNorm is actually written by this guy in the USA, a Polish guy called Piotr Zelasko. He wasn't in university. He's now working in a company, but he's still very active in this stuff. And we also have a bunch of contributors from outside Xiaomi, like just open source contributors. Now, right now in the recipes in Icefall, we're mostly working with RNN-T. And technically, it's not an RNN. It's not, because we don't really use LSTMs right now. We're mostly using transformers. So technically it's a transducer, but we use the word RNN-T because that's what it's called. So Icefall doesn't have any Kaldi dependency. It just depends on PyTorch, although it does depend on these other repositories, K2 and LayerNorm. right now, we put a lot of effort into fast RNN-T training. We're focused on things that can be practical to build real speech recognition systems. And we're also working on another project called Sherpa that has the runtime, like so that you can build a server that does real-time recognition, things like that. But this is in a very early stage. So to compare Next-Gen Kaldi with other popular toolkits, probably the most popular kind of PyTorch-based toolkits, or most popular Python-based toolkits for speech recognition right now are SpeechBrain, ESPNet, and WeNet, although there are others. Compared to SpeechBrain and ESPNet, we're much more focused on just speech recognition. Though those projects have quite a wide range of interests, including TTS and speech separation. Right now, we're just focusing on ASR, and our main focus is to be something practical that companies can use to build real speech recognition systems. And I don't want to say that this is ready. This is not 100% ready yet, because we have not finished. We have not finished all the issues about real-time recognition, but we're working very hard on it right now. We're different from WeNet because we don't have any Kaldi dependency. We're trying to build everything kind of from scratch. Although it's based on PyTorch, so it's not totally from scratch. But you know, we're taking inspiration from these other projects too. We've used code from ESPNet, from WeNet. Okay. So the basic vision of Next-Gen Kaldi is to have low latency speech recognition that's accurate, that has high throughput, so you can do the server inference very efficiently. This is something that the other big toolkits, SpeechBrain and ESPNet, are not focused on at all, as far as I can tell. Another thing we need, so we want to be able to use this in all of Xiaomi's products, as well as being open source, right? So there's certain requirements. Apart from the high throughput and low latency, we also need to support contextualization. For example, if you have names of contacts, or you have a database of music song titles, you need to be able to somehow put that into the system. And also to specialize it to particular products, like suppose you have an air conditioner or something that has certain commands. This is something that so-called end-to-end speech recognition is not very good at. Like, people can get super impressive numbers on LibreSpeech with RNN-T or with transformer transducers, but when you try to actually build a product with these things, you realize that there's actually a lot of problems with it. So anyway, I'm very committed to getting something working. This has taken a lot longer than expected, but at some point, you know, we're really going to have something working, and I hope that's going to be by the end of the year. So, like I said, we were hoping that we would have already released something like a year ago, and I've never been very good at estimating timelines. And I guess I didn't take into account how long it would take to build up a team and to learn the things needed, because I was always coding in C++ and CUDA. I was never a very big Python programmer, so I had to learn a lot of things. And also, we've changed direction quite a lot, because originally, the plan was to keep most of the Kaldi code, but use PyTorch for the neural net stuff. But in the end, I decided that it was just going to be too much code. It was going to be too much legacy. And I decided it was not a good plan. And the next plan was we built K2 with the intention of focusing mostly on finite state automata, things like lattice-free MMI, CTC. But we couldn't quite get the word error rate results that we were hoping for from that. Now, K2 is still is still very useful because for a start, you can use finite state automata for a lot of things, like lattices are a data structure that you're going to need for any serious speech recognition system. And secondly, the way we built K2, it's based on these primitives called ragged tensors, which is a very useful data structure for implementing algorithms on GPU that have irregular structure. So let's say fast RNN-T, we used some utilities from K2 to build that. And RNN-T decoding, we also used K2. It's some very useful primitives there. So even though we switched focus a little bit from lattice-free MMI to RNN-T, it's still very useful. So this is the middle part of this talk. I'm going to briefly go through some of our work on accelerating RNN-T. And then we're going to get into the transformer stuff. So there's a challenge with RNN-T if you want to build a large system, especially on a language like Chinese. Let's suppose you want to build a Chinese system with the characters as the units. It's actually too slow to do standard RNN-T. The problem is that you have this 2D recursion over frames and the different positions in the transcript. And each position in this recursion involves the whole vocabulary size. It involves a big matrix multiplication. So if the vocabulary is like 6,000, it's too slow. You can't really do it. So our basic idea is we don't really need to do the computation over the entire matrix of sequence length versus acoustic sequence length, because most positions in that matrix don't really contribute to the loss function. So if you look at that figure that says B, the contribution to the derivative or to the loss, it's only non-zero along a diagonal, like of the time by sequence position. So if you can just focus on that diagonal, you can make it much faster. So basically, the way we're doing this is to use a simpler version of the RNN-T encoder, where the so-called joiner is just adding two vectors and renormalizing. And with that simple version, we discover what's the important positions, and then we just do the big version with the positions that we need to do. So this is some tables from our paper showing that our thing is much faster and uses a lot less memory than the standard thing. And also we have better word error rate. The reason we can be better is because I mentioned that we have like a simpler version of the RNN-T joiner. So we can use that for regularization. It's another part in the loss function. So the word error rates get a little bit better. Okay. So this next part of the talk, this other thing that we did is about speeding up decoding for RNN-T. So in traditional RNN-T decoding, on each frame of the acoustic input, you can output an unlimited number of symbols. Actually, sometimes RNN-T systems can get into a loop where they emit the same symbol over and over. So you have to find a way to stop that from happening. But in practice, in a well-trained RNN-T system, what we find is that it almost never emits more than one symbol per frame. Now, this does depend on the frame rate. We have 25 frames per second. So in 25 frames per second on Libre speech, it basically never emits more than one symbol per frame in test time. We actually tried a modified version of the RNN-T, where even in training time, you can only have one symbol per frame. And for some reason, that actually did not work. So for some reason, even though in inference, you never have more than one symbol per frame, you actually need it in training. But anyway, so the way that we speed up RNN-T decoding is we limit it to one symbol per frame. And then we use our K2 ragged tensor things to do the whole thing fast in parallel on the GPU. And this again is some graph from our paper showing that our thing is super fast. And we have a few comparisons. This 25% modified thing is, remember I said that in training time, if you have only one symbol per frame, it doesn't work so well. Well, if we have an interpolated loss function where we just use 25% of that one symbol per frame, that works okay. And that acts as a kind of penalty to prevent it from emitting more than one symbol per frame in inference, so that we can be guaranteed that it's not going to affect the word error rate results too badly. Anyway, so that's that. So this is the last part of the talk, and the part that's a little bit more technical, I guess. I hope it's going to be interesting to you guys. This is about our reworked conformer model. So the conformer is just the latest version of the transformer that everyone is using in speech recognition. And what it is it's just the transformer plus a convolution module. But so our reworked conformer is the conformer with a lot of changes that I'm going to describe below. And it allows us to have faster training and more stable training and slightly better word error rate. But I think the main reason I think you'll be interested in this talk is that we have some insights about things that can go wrong with transformer training. So here is a picture of the conformer encoder. This is the main part of the transformer. Yeah, it's a modified transformer. So in each layer, in each module, we have a feed forward module, then self-attention, then a convolution module, then feed forward. So if you just have the first two, the bottom two, that would be a standard transformer. Now, so the red part in this diagram is the LayerNorm. We use so-called pre-norm, that at the start of each module, there's a LayerNorm, and also at the output of the whole layer, there's a LayerNorm. Okay, so former BatchNorm inside the convolution module. And also we were using BatchNorm at the input to our, we were originally using BatchNorm at the input to the whole thing to normalize the speech features. Now, so I'm saying that BatchNorm should be considered harmful. And here's the reason. BatchNorm itself works great, like there's no problem with it. But the problem is, if you do anything unusual, BatchNorm is going to create a lot of problems. So if you group the training utterances by length, that's going to be a problem for BatchNorm, because BatchNorm has this assumption that the elements of the mini batch are sampled independently. So if you do something like you group the utterances by length, or maybe you have two different data sets and you want to do them in different mini batches for some reason, this is going to cause a lot of problems with BatchNorm. Basically, it's going to affect your results because it's a train test mismatch. That in training time, your model is seeing utterances that are grouped in a non-random way. And then in test time, because we use the average BatchNorm stats, it's as if the utterances are grouped randomly, and it will affect the results. Also, if you do fine tuning on a different type of data, it's going to be a problem. It's actually ironic because in the original BatchNorm paper, they say it's a solution to covariate shift, and covariate shift just means that you have a different type of data that has, you know, different distribution. So this is actually the thing that BatchNorm cannot deal with, that if you have a different data distribution on different parts of your training and you separate them, actually BatchNorm is really bad at dealing with that. So anyway, my position is that if possible, it's going to save you a lot of headache if you just take BatchNorm out of the model. So one of the first changes we made to the model is to just replace BatchNorm with LayerNorm in the convolution module and also for the input to the network. And in the input of the network, actually, instead of LayerNorm, we just replaced it with a scale of 0.1. So the reason that's necessary is because the log-mel features have a very high dynamic range, like -20 to 0. And because that's so large, the bias parameters cannot really get large enough to be comparable to that. Like if you multiply this -20 to 0 by a weight, it's still going to be large, and the bias can't train big enough. So we just replace it with a scale. Now, a lot of you are probably thinking, why are you using log-mel features? Everyone is using the waveform. Now, a lot of people do use the waveform as an input, and of course it's great to use that, but it doesn't really give you any advantage. A lot of people have published papers in conferences like NIPS saying, oh, we have this thing and it's better than log-mel Kepstrom. But usually there's some problem with how they did that comparison. And whenever anyone does like a reasonable comparison, it turns out it's not really better. Now, this may not always be true. Maybe in future, someone is going to really show that it's better to use waveform. But we use filter banks because they're more compressible and you can load them much faster from disk. Otherwise, you become limited by I/O. Anyway, so the next thing is we'd like to remove LayerNorm. Like if you look at this this model, it seems like there's too much LayerNorm. So let me get into why we need LayerNorm, and I'll maybe be able to explain why I think it has too much LayerNorm. So let's recap what LayerNorm is. So LayerNorm is just a formula applied to a vector that could be like one frame of speech or one pixel of an image. So it has 3 stages. We remove the mean, which is actually a waste of time in most cases. We normalize the length of the vector, and there's an epsilon in that formula. And then we apply a learned per dimension scale and offset. And this is the same as in BatchNorm, like a weight and a bias. Now, why do we need LayerNorm? So in a deep model, unless you normalize every so often, eventually the activations are going to become like infinity or 0. And then your training is not going to be stable. It's gonna fail. So in addition to the normalization, the learnable per dimension scales, the gamma, those help to balance the size of the activations and the relative contributions of the different modules. So there's 4 modules per layer, right, in the conformer. Now, we want to be able to scale up or scale down each individual layer. And it's very hard to do that by learning the size of the weight matrices of the layers, because they're so large that to scale them down, you're basically trying to learn a very high dimensional direction, right? It's too hard to learn. So it's much easier if you have like a separate scale, like the per dimension scale in BatchNorm, that you can just scale down the output of that module to balance the contribution of those four things. So that formula shows you how, just due to the noise of the gradient noise from each mini batch, this is how the size of the weight matrix will change over during training naturally. If the learning rate is constant, it'll follow like a square root of t line. And actually, if you look at the weights in transformer models, you'll see that they're quite close to this formula. Now, this formula is only valid if the optimizer is Adam with no weight decay. With weight decay, you have to compensate. But the point is, it's better to just let the weight matrix naturally do its thing and get larger and larger, and have something else that's going to scale it down. And that's where the BatchNorm or LayerNorm comes in. Now, there's certain bad things that can happen during transformer training. In our Icefall, we implemented a lot of diagnostics, like, so PyTorch has these forward hooks and backward hooks that you can add. So it's possible to use those to accumulate a bunch of statistics to tell you like how big the outputs of the different modules are. Now, so that's how we discovered certain problems that can happen in transformer training. So you can get whole modules dying. So this means that, let's say one of the feed forward modules, after training, you'll see that the output of the module is almost zero. It's like 10 to the minus 6, something like that. And that seems to be something that happens with the BatchNorm weights. So if early in training that module was not useful, the BatchNorm weights go almost to 0 to turn it off. And the problem is, if the BatchNorm weights are oscillating around 0, they're becoming positive then negative. The module never learns anything useful because the sign of the gradient is constantly flipping, right? So it doesn't know which direction to learn. So basically, in that case, the module never learns anything. And this happens particularly for the lower down feed forward layers. It can happen for quite a few of them. Now, there's another odd or undesirable thing, perhaps, that happens with LayerNorm, that especially in the middle of the network, after training the model, we notice that often one channel out of the, let's say, 512 or 256, one channel gets very large and constant. So you look at the activation and it's, let's say, negative 51 plus or minus 1. So it's almost constant. Now, the individual modules don't really see this large activation because it gets scaled down by their input input layer norms. And my belief is that the reason the system does this, the reason it learns this large value, is it doesn't want to get layer normed. So LayerNorm removes the length information, right, from the vector, because it normalizes the length. The model doesn't want that, so it adds this large constant value, which functions like a very large epsilon in that formula, and that means that the length of the length of the rest of the vector elements, excluding that one large value, is almost constant at the output of the LayerNorm. So we're going to use this insight to help to replace LayerNorm and to fix this problem. So this negative large value is going to be a problem if you want to use let's say integerization. If you want to use 8-bit activations, it's going to be a problem to have this big large value. So so here's how we removed LayerNorm. there's a few things that we had to change. Firstly, remove LayerNorm at the inputs of the modules. And at the output of the whole layer, we replace it with something called basic norm. So basic norm is just we normalize the length of the vector, but we normalize it with a large epsilon. So this epsilon, like we initialize it to 1 and we learn it in log space. So in the end, it's going to be like 2 or 4 or 5 or something. So what that does is that because the square root inside it is dominated by the epsilon, the output vector length doesn't strongly depend on the input vector length. We know that it's going to be shorter than 1, but sorry. The output vector length does depend on the input vector length, meaning if the input vector is longer, the output is going to be longer. Now, because we need to balance the contribution of the different modules and we don't have the learnable weight, we modify all our weights and biases by, instead of self.weight, we use self.weights times weight scale.exp. So we're multiplying it by a learned scale, but that scale can only be positive. And it's important that it should only be positive, because otherwise we can get the oscillating gradient problem that I mentioned before. So if the scale is going negative, positive, negative, positive, we never learn anything because the gradient keeps flipping. Okay, so that's how we remove LayerNorm. Now, we made some other changes to the model too. So there's another failure mode, or another bad thing that can happen during model training, is inside the feed-forward modules, and there's 2 feed-forward modules per layer. A lot of neurons can die. And what that means is there's a hidden dimension inside the feed-forward. Let's say it can be 2048. We might find that 10% or even 50%, even 80% of those neurons are always negative. Now, the activation is very similar to ReLU. It's actually something called Swish, but it's ReLU-like. And if the activations are always negative, the output is always 0, or at least always close to 0. So it's not doing anything useful. So we have a way to fix this by modifying the gradients. I'll explain it later. There is another failure mode that's less common. Again, we discovered this by looking at the diagnostics that I mentioned. So the actual activation inside the feed-forward modules, and also the convolution module, is something called Swish, that in PyTorch it's called SILU. It's just x times sigmoid of x. Now, if the model is well trained, you'll see that the normal magnitude of the input to this SILU will be between about 1 and 3. That's the root mean square value of a dimension. Now, there's 2 ways that the model cannot train properly. One is if the inputs become too small, like 10 to the minus 4, 10 to the minus 5, the function is almost linear. Like if you scale up the function, it's just y equals x. And in that case, it's not learning anything useful. There's no nonlinearity. The other problem is the inputs to the function can become very large, like 100. In that case, it's just the same as ReLU, because if you zoom out from that, it's the same as ReLU. And that's not optimal because ReLU is not quite as good as this Swish. So again, this is something that we're going to fix by detecting it and messing with the gradients. So yeah, our solution to both of these problems that I mentioned just now is something called the ActivationBalancer. So this is a module that does nothing in the forward pass. In the forward pass, it's just y equals x. And in the backward pass, it's going to modify the gradients a little bit. Now we place this module just before the nonlinearity, meaning just before the Swish. And what this module does is, in the forward pass, it does nothing, but it accumulates some statistics and it works out which channel dimensions are problematic. And problematic means, for instance, less than 5% of the values are more than 0. This 5% number actually comes from Kaldi. We used to do the same thing in Kaldi. So for those dimensions, we want to penalize them if they're negative. Now, what we discovered in early experiments is that if you just add a penalty to the loss function, what the model does is it just concentrates all the positive values in the padding frames, because the utterances have different lengths, right? We have to pad with 0. So the model learns to just make those padding frames very positive. So that's not what we want. So instead, we fix this by modifying the backpropagated derivatives by multiplying them by 1 plus epsilon or 1 minus epsilon. And which one we choose depends on the sign of the input and also the sign of the derivative. This, you can work out what the rule is. It's quite simple. And we also use a similar approach for the wrong magnitude problem. Like if the mean absolute value is less than 0.2 or more than 10 or something, we can use the same kind of formula with epsilon to encourage the inputs to have the magnitude that we want. Now, there's also something quite cute that we discovered accidentally. So at some point, I had a bug in some script that was applying the swish nonlinearity twice. And I noticed that the experiment was a little bit better. Like after I fixed that, it got worse. So I'm like, why is that? So it turns out that it's actually a better nonlinearity. I'm calling it DoubleSwish because it's just swish of x, but you can approximate that function by x times sigmoid of x minus 1. It's an almost identical function. If you look at that figure, those two lines very close together, one is one and one is the other. So we're actually using this sigmoid of x minus 1 times x. It gives a very small improvement. It's like 0.1% whatever rate, but we've validated it in a few different setups, and it seems to be consistent and real. Yeah, so this is just a larger version of the figure showing the new nonlinear. It's not just a scaled version of swish. It's actually it's qualitatively different because the derivative at 0 is 1/4 instead of 1/2. And eventually it becomes just linear, like y equals x, but the behavior around 0 is different. So, okay. So there's another problem that we fixed, and you can argue that maybe this is not a problem, but I didn't like it. So as I mentioned before, the parameter tensors will naturally grow throughout training. Just because each iteration gives you gradient noise, and that gradient noise adds up during the entire training. Now, one way to fix this is just to use the learnable scales in BatchNorm and LayerNorm to scale things down. And that kind of works, but eventually it can become unstable because once those BatchNorm or LayerNorm scales get very close to 0, the output can become too sensitive to them because the big tensors are too large. So eventually, after training many iterations, your transformer or conformer can suddenly become unstable and go to infinity. Another reason I don't like these growing parameter tensors is it makes the learning rate schedule very hard to interpret. Because what can happen is that even though the learning rate is growing, you're actually learning slower and slower in relative terms because the parameter matrix size is growing even faster than the learning rate. So yeah. So our solution to these varying parameter norms is we just limit the root mean square value of all non-scalar tensors to 0.1. And we do this by, if it gets larger than that threshold, we start to apply weight decay. So this is just a change to Adam. So if you take Adam W, which is just add them with shrinkage instead of for the weight decay. So instead of modifying the gradients, you just shrink the whole parameter matrix. That's Adam W. So we change that to Eve, which is we only apply the shrinkage after you get root mean square more than 0.1. So this makes the learning schedule much easier to interpret. But we also, sorry, we also have to use a different learning rate schedule because the conventional one doesn't work anymore, right? So we have to decay it more aggressively for large T. So here is the standard learning rate schedule for transformers. It's something called a GNOME, or sometimes people call it just a transformer learning rate schedule. So it starts to increase linearly, and then it decreases as 1 over square root of T. And what you'll find is if you try to train a transformer using a conventional learning rate schedule, it just won't train. It will never learn anything. I mean, certainly that's true for speech in our experience. So we actually, as part of this rework of the conformer, we're removing the warm-up period. And instead of warm-up, we implement warm-up at the model level. So that arrow around the side, the curved arrow there in the picture, that's indicating a layer level bypass. So what we do is we have this constant called a warm-up that we feed it into the model, and it begins at 0 and increases to 1, and then it stays at 1. So for the first 3,000 iterations, this warm-up is increasing. And basically, for each layer, we bypass the layer proportional to warm-up. So look at that formula there, 1 minus warm-up. Oh, sorry. I'm trying to highlight that, but it's not working. We return 1 minus warm-up times input plus warm-up times output. So effectively, if warm-up is close to 0, the model acts like a very shallow model, and it's much easier to learn. And after we make this change to do the model level warm-up and use a different learning rate schedule, we find it optimizes way faster. So our learning rate schedule that we, after tuning this, here is what we came up with. I'm putting in like actual constants. These are obviously tunable, but if n is the epoch and t is the mini batch from the very start of training, including all epochs, this is the formula. It starts off approximately constant, then it becomes like 1 over square root of t, and then eventually it decreases like 1 over t. And the reason we make it dependent on both the mini batch index and also the epoch index is it gives us a better kind of invariance when we change the mini batch size or the number of workers. So basically, we want to have about the same rate of progress per epoch, regardless of how many workers we have. So if we have more workers, we want to learn a little bit faster per mini batch. And this formula gives us the right kind of invariance. So the idea is we just tune it once, and then when we change the number of workers or the mini batch size, we don't have to retune it. So this figure just compares, the red one is our formula, and the orange one is the standard transformer learning rate schedule. You cannot really, in a sense, you cannot really compare these two because they're intended for different types of model. Our thing is with the fixed parameter norms. So in reality, the transformer learning rate schedule is decaying faster than that because the matrices are getting larger, so the relative change is smaller. We did notice that after you fix the parameter norms, the learning speed becomes much more sensitive to the exact learning rate schedule. The reason for this is that if you don't fix the parameter norms, if you use a larger learning rate, your parameter matrices get larger, right? So the relative change in learning rate is smaller. And in fact, if you multiply the whole learning rate schedule by 2, you'll train faster initially, but for large T, you're actually training about the same speed, because eventually the parameter matrices will just be twice larger approximately. And it turns out you can do some analysis on this using the formula that I mentioned previously. Even if you have a T to the P type schedule, even if you change that power, if you think about if you work out the relative learning rate, in theory, you're really just changing it by a constant factor for large T. This is true only for P is greater than minus 0.5. You can work out this from the formula that I mentioned a few slides earlier. Oh, I can't find the slide. It's that formula with a square root in it. So anyway, the point is that even though the transformer learning rate schedule looks very weird, it's actually not as weird as it looks, because even while the learning rate is increasing, it's actually learning slower and slower. At least once it grows beyond the initial parameter size. So this graph shows the speed of convergence of our new model in blue compared to the old model in orange, and you can see that for the first part of training, we're training way faster, like 10 times faster or more, because we don't have this warm-up period and we have this model level warm-up. It's way faster, and even later on we're still faster. It's like maybe twice faster, or at least 60% faster. Sorry, I mean 40% faster, something like that. So we also have some small width error rate improvements. Unfortunately, so all the things I mentioned above, I tuned those on a smaller subset, like LibreSpeech 100, and it turns out that not all of those changes are fully additive. But when we test the whole thing on LibreSpeech, on full LibreSpeech, we still get an improvement. And the main improvement of all of these things is the recipe is more stable and it's way faster. Like, for a start, we don't need so many epochs. We're using like 30 epochs instead of 60. And also per epoch, it's a little bit faster because we took out all of those layer norms. Plus it's more stable. So we're also working on a further improved version of this optimizer, where we use the scatter of the gradients to do a change in coordinates before we do Adam. So because Adam is per element, if you rotate the parameter space, it actually is going to change. It's going to change how it behaves. So, but I'm not going to describe that right now. It's not really finished. Okay, so this is just a summary of what I've said before, so that to help you guys remember it. First, I had this argument that BatchNorm should be considered harmful because it causes hassles for things like fine tuning and data loaders. Second, we replaced the LayerNorm with this basic norm that's just length normalization with a learnable epsilon. Because we took out the learnable scales from LayerNorm from most of the modules, we make everything learnable by having this weight scale thing, and it has to be positive to prevent that oscillating sign problem that I mentioned. We fix a bunch of different problems with this activation balancer. We're detecting dead neurons. We're just detecting values that are too small or too large. To make the learning rate schedule more interpretable and to make everything more predictable, we're limiting the root mean square value of all the non-scalar parameter matrices to 0.1. So we fixed the size of all the matrices. we're doing model warm up in a different, we're doing warm up in a different way. We have this learnable, not learnable, we have this variable bypass of all the layers to help it to train early in training to help it to converge. We have a new learning rate schedule with no warm up with a different formula. And we found that replacing swish with DoubleSwish is helpful. Oh, and that link there is just to the recipe in our repository that has all of these changes. We've actually made some further changes later on. So we're up to like pruned transducer stateless 5 or 6 now, because we've improved the recipe in other ways, but this is the first place that we used all this. Okay, so that's pretty much my talk. We can now have questions. I think I've gone through it a little bit faster, but maybe it'll help us to get back on schedule. That link is to a WeChat group for discussing Next-Gen Kaldi. If you're interested, you may be able to get one of these T-shirts. And those are just links to our main the main links, our main open source repositories. We have other ones too, but probably Icefall is the top level, you know, the recipes, and then that will download the other ones. So let me try to find the correct window so I can see if there's any questions. I have to, okay.
Excuse me, Daniel. Wait a minute. Yeah, I need to introduce the another invited professor to give you some interaction. Okay, sure. And yeah, first, very thank you. Appreciate this talk. Very, I think it summarized a lot of insight in very detail, and I believe they can be rethink and resound and leverage even for the other area. Thank you. And so let me introduce the Professor Qin Kelvin, and he is he actually has worked for IBM Research more than 25 years and has led the speech team and languaging for a while. And he, last year he joined Nankai University as the distinguished professor. So I will switch to Kelvin, Professor Qin, to raise the question and include those questions from our broadcast channel. A lot of audience raised the question actually. Okay, thank you.
Yeah, hi Dan, how are you? Long time no see.
Yeah.
So thank you very much for your very technical briefing about RNN-T and also the new work on conformer model. I think there are a few questions from the society. The first one is, in my understanding, the person who is working on smartphone device, I guess it is a, he want to have some embedding model, small model basically. So he's asking whether Kaldi has any plan, maybe K2 has any plan to, to compress the model, to do some quantization.
Yeah, well, we definitely have a plan to do that. I don't think that's going to be happening over the next like 2 or 3 months, like maybe in like 4 months to 8 months. I think we're gonna start considering that. I mean, it's an issue for Xiaomi's products too. So we're probably going to end up using some framework that like there are certain frameworks, even Xiaomi has one called Mace for deploying on things like smartphones.
Okay, okay.
And there's also, like, I know PyTorch has things to do with integer quantization, but we haven't really started playing with that. We're going to get to that at some point though.
Okay, thank you.
Yeah.
The second question, I have a similar question with the question 4 from society. Basically, you mentioned the VNet, and also in my understanding, there are a lot of local, speech company today, they are using VNet to do the product level deployment. So my question is, what's the major difference in your idea, between K2 and VNet?
Well, I mean, I think the goals are pretty pretty similar. Like we're we're making some different technical decisions. Instead of using existing Kaldi tools, we're trying to kind of start from scratch. So I guess we're a little bit less mature than WeNet right now, meaning like if you want to actually build a practical system now, WeNet is probably a good choice. But if you're, if you have, your team has some extra bandwidth and you're interested in like, what's going to be the next models or like what the future will bring that's going to be even better, maybe you can look into our tools.
Okay.
Yeah.
Yeah, thank
you. So
thank
we
you.
are aiming to we are aiming to get better word error rates than WeNet and everything, and we do already on some databases, but we're a little bit less mature right now in terms of real deployment.
Okay. So I have several master students and the PhD students. I will definitely ask them to learn K2.
Sure.
Okay. One more question about K2. In VNet, they are using WFST to integrate the language model, right? Yeah. So what's your plan for K2 to integrate the language model?
Well, we are planning, I guess, in the short or medium term is to use WFSTs probably to like combine those with RNN-T decoding. We've already implemented like FST based RNN-T decoding. Okay. Perhaps in the longer term, we might try to go for a more flexible setup where you can like contextualize your model in different ways, maybe using a neural LM. But I think probably in the short term, it'll mostly be WFSTs. Okay, got it. One more question from myself.
Today, when they have few number of training data, people will use the data augmentation.
Yeah.
So in your K2, there are a lot of data augmentation methods, for example, speed perturbation, timing masker, frequency masker, etc. What's your belief, which kind of data augmentation is more effective?
Well, right now we're using all of those that you mentioned. We're using the kind of the speed perturbation like in Kaldi, but we're also using spec augment, which is the time and frequency masking. Yeah. So something else we're doing is like we have some recipes where we have different RNN-T heads like joiners and decoders on top of the encoders, so we can use different databases with possibly different like vocabulary sizes that have different RNN-T heads. So that would mean that even if you have different languages of training data or like they're prepared in a different way, you can train one model with multiple different databases. So that would mean that you can combine with like mismatched data more easily.
Yeah, okay. Last question. Today you talk about RNN-T and also some improvements on conformer model. Yeah. So in terms of the future plan of K2, which one is the major stream, RNN-T or conformer?
Well, it's not really an either or, because the conformer is the encoder that we're using for RNN-T. So, so when I say RNN-T, I'm really just talking about the loss function and the top of the model. The actual, the RNN-T also has like an encoder. I don't, maybe that's not the word they use. I think it's an encoder. But so instead of using an LSTM, we're using a conformer encoder.
Okay, got it.
Now we are actually interested in LSTMs too, because conformers are not naturally streaming. So we're working along two lines. One is we're doing something like WeNet, where we have like chunk by chunk conformer evaluation. And the other is we're going to investigate LSTMs, and maybe we can train the LSTMs from like teacher student from the conformer, something like that. So we're investigating both of those.
Okay. Maybe one more last question from the society. a student is asking, dear professor, what's the most famous toolkits for ASR? If I want to only focus on ASR, do you have any suggestion which toolkits is more easy to start, easy to use?
Well, I mean, I'm assuming that you've used PyTorch, right? So
Yes.
with any of these toolkits, you're probably going to need a server that has like at least one GPU and that and like fast disk and a lot of storage and a good enough internet connection that you can download some training data. But
Yeah.
I don't know, maybe SpeechBrain would be like easy to start with.
Okay.
Yeah.
SpeechBrain. Okay. Okay. Thank you so much,
Cool.
Dan.
Thanks.
And also looking forward, for you to visit Nankai University.
Cool.
I have a
Thanks.
team in that university,
Cool.
focus on speech. Okay.
Cool. Bye.
Bye. Bye.
Thank you, Professor Qin. And Daniel, can you? Oh,
Yes,
sorry.
sure. Yeah.
Yeah. Can you share your last page? And because our audience want to scan the code, the QR code to join the.
Oh, sorry. Okay.
Yeah.
Let me. Can you see it now?
Just do it again. Yes. So actually, we have a lot of other questions related to your talk, but we don't have enough time to answer that. So just to let the people to
okay, maybe we can answer them
again.
in the group, but make sure to send me the question so I can answer them.
Sure. Thanks again.
Bye.
Thanks a lot for your time for today's talk. Okay.
Bye.